Unit 9, primitives. So with this we start integral calculus, which is in a sense like the mirror part of differential calculus. So in differential calculus we asked, what is the measure of how fast a function is increasing or decreasing, right? And that's the derivative. And further derivatives gives a sense of how this increase is increasing. Okay, so how this curvature of the function is changing. Okay, and we ended up with our Taylor expansions with kind of put together all the information from many derivatives to tell a story about functions around certain points, right? Now, the we can ask ourselves, well, if we have a function, right? We know that if we compute the derivative, we find another function, right? The derivative of that function. Can we, if we know the other function, can we go back to the original function? Okay, is there any operation like subtraction and addition or multiplication and division? Is there an operation that allows us to go back to the original function? And that's what we call a primitive. Okay, so, and you may have heard this as indefinite integrals before. So this has a relationship with integrals, but I like to call them primitives because so far we're not talking about integrals, which are kind of a type of sums. We'll deal with integrals in unit 10, right? But for now, we'll call we're talking about primitives, and so we say that a function capital F is a primitive of f of small f if the derivative of capital F is small f. Okay, so and we denote this operation the primitive of f is capital F. Okay, and this is the sign for the integral in general. So this is an S for the sum, okay, because integrals are sums. But this is kind of like the spoiler of the movie because the relationship between primitives and integrals comes later. Okay, for now we just are worrying about if we have a function f, a function capital F, and then I go to f using the derivative, right? Then what's the operation that goes back? Okay, and this is the primitive. Okay. Now, in unit 7, we saw that if two functions, let's say function f and g, have the same derivative, right? Then they're similar, they're equal to each other except for a constant, right? That means that f is equal to g plus k, where k is a constant. Okay? So if you don't remember about this, review unit 7. Okay? That's one of the corollaries to the mean value theorem. So that means that the primitives to any function, right, are unique up to a constant, right? So if you have a function, if f is the primitive of f, small f, g can also be a primitive of small f and be different from f, but then the relationship between these two is that there is a constant that equals both of them, right? Now, because the primitives are like the opposite operation of the derivative, then that means that the primitives obey the same linear rules as the derivatives do. So, for instance, the primitive of this function af plus bg, and we say dx, which we'll see what this means when we get to integrals next unit. This is equal to a times the primitive of x, f, plus b times the primitive of g. Okay, so this is capital F, this is capital G, for instance, right? And this is easy to see, right? So if af plus bg, we compute the derivative of this, then this is a derivative of f, b the derivative of g, but this is small f and this is small g. Okay, so you can see how we get from this to the other, right? Now, From this definition, seeing that the derivative is so the primitive is the inverse of the or the reverse of the derivative, then we can see many kind of elementary primitives, right? That you need to know by heart, right? So if we have x to the alpha when alpha is different than -1, then the primitive is x to the alpha plus 1 divided by alpha plus 1, and it's easy to see because if you differentiate this, you have x to the alpha, right, times alpha plus 1, and then divided by alpha plus 1 you get 1, right? So that's what you get. 1 over x, or x to the -1, the primitive of this is the logarithm of the absolute value of x, and because if you compute the derivative of the logarithm you get 1 over x, right? And the exponential is the same. A to the x is a to the x divided by the logarithm of x, because the derivative of a to the x is a to the x times the logarithm of a, right? Now the primitive of the sine is minus the cosine, because the derivative of the cosine is minus the sine. The primitive of the cosine is the sine, because the derivative of the sine is the cosine. The hyperbolic sine and the hyperbolic cosine are primitives of each other. And then these are two interesting ones. 1 over 1 plus x squared is the primitive of this is the arctangent, right? And 1 divided by the square root of 1 minus x squared, the primitive of this is the arcsine. Now the primitive of the tangent is 1 over the cosine squared, and the primitive of the hyperbolic tangent, it's the other way around, sorry. The primitive of 1 over the cosine squared of x is the tangent, and the primitive of 1 over the cosine, hyperbolic cosine squared is the tangent, hyperbolic tangent. Okay? So you need to know all of them. Now, some primitives, they're not as straightforward as those elementary that we have seen, but all of them have this form, right? You have the derivative of f at g times the derivative of g, right? So this follows the chain rule, right? You have f at g, the f composed with g, right? The derivative of this is f prime at g times the derivative of g, right? So if you have this form, it's easy to go back to the original one, right? So because it's easy, we call these immediate integrals or primitives, right? And some example of those are, for instance, if you have g prime divided by g, okay? The primitive of this is the logarithm of the absolute value of g plus c, right? Always a constant, because you never know. You have the primitive of g prime divided by g squared. This is the arctangent of g, right? Plus a constant. Now if you have g prime times g to the alpha, right? Then this is equal to g to the alpha plus 1 divided by alpha plus 1 plus c. Okay, you see, right? In all of these cases, if you differentiate this side, you get this, right? So it's easy to see. And then, for instance, g prime divided by the square root of 1 minus g squared is the arcsine of g. Okay, some examples of this. Okay. So let's see some more examples of immediate primitives, okay, and how to compute them. So for instance, let's see, we have the tangent, the primitive of the tangent, right? And let's say it's 1 over the cosine square, something like that, right? So the primitive of the tangent, what we have to realize is that this is the sine divided by the cosine. And so remember that we have just said that we have a primitive of this form is the logarithm of the absolute value of g, right, plus c. Now in this case, we have g, right? G is the cosine, and g prime is minus the sine, right? So this is almost this primitive. So this is just minus, we multiply it by minus 1, and then we get this. And now this is the logarithm of this the cosine. So this is minus the logarithm of the absolute value of the cosine plus c. Okay, that's the primitive of the tangent. Okay. And you can see easily that using the same argument to the cotangent, which is the cosine divided by the sine. Now in this case we have the sine here, and the derivative of the sine is the cosine, so this is directly the logarithm of the sine. Okay, so remember these two, or if you don't remember them, at least remember how to find them easily. Okay, and then we have another interesting example, which is more difficult, but it's interesting to compare with this. So this is the primitive of the second. Okay, and the second, remember, is 1 over the cosine of x, right? Now here it's kind of similar from before, right? But we lack the g prime on top, so we're going to want to do some manipulations here in order to get something that is the logarithm of something. Okay, so bear with me, right? The derivative of the second, right, is going to be the cosine squared, right? And then we have minus this derivative of this, so minus the sine, right? And this is sine divided by cosine, the tangent, times the second, right? So this is sine over cosine times 1 over cosine, right? Now, but the derivative of the tangent, we know, is 1 over the cosine squared, right? Or in other words, the second squared. Right? So if we add these two, right, we have the derivative of the sum between the second and the tangent. We have let's see, the tangent times the second plus the second squared, or in other words, we can take common factor second squared, and we have, sorry, not second squared, sorry, second only, and we have the tangent plus the second, right? But wait a minute, this and this is the same, so we can say that the second is equal to the second of x plus the tangent derivative divided by the second plus the tangent. But now the primitive of this, if we compute the primitive, right, the primitive of this is just the logarithm of this, right, of the absolute value of this. But this is exactly equal to the primitive of the second, right? So if we write it here, this is the logarithm of the absolute value of the second plus the tangent plus c. And you can also write this, if you want, this is 1 plus the sine divided by the cosine. Okay, both ways are correct if you don't like one of the two, right? Plus the sine. Okay, so yeah, you're not expected to come up with this kind of reasoning, but just so you understand how to compute this thing. Okay, and so that's an interesting, you'll see it's going to be a very interesting primitive to know in some of the problems. And so knowing this, it's easy to see that this is going to be, this is the primitive of the cosecant, right? It's 1 over the sine of x. So I leave it to you to try it at home to prove that this is equal, the primitive of this is equal to the logarithm of the cosecant plus the cotangent, right? Or in other words, you can write it like this, the logarithm of the sine divided by 1 plus the cosine, okay, plus c. Okay?